Hi, everyone. Hope you're having a great time today so far, post-Halloween. So I'm going to talk about machine learning for identity resolution. And we're going to go into some detail. We'll have a good demo later on about some of the combination we have of Hopsworks and Infrix. Just a little bit about us, Hopsworks, before we get started. Hopsworks is a company that built the first original or OG feature store for machine learning. It's also a complete data science platform, so for developing and operating machine learning systems. So it also includes a model registry and model serving. But primarily it's used at very large organizations as the data layer for AI. And you can see some quotes from some of our customers there. I'm going to hand over to Yogesh to present Infrix.
Sure. Thank you, Jim. Hi, everyone. This is Yogesh. So basically, Infrix is a low-code application development accelerator to build, machine learning AI type of applications without writing any line of code. There are some of the use cases which are listed here in the area of customer analytics, risk analytics, and fraud analytics. And today we are going to present the use case, which is the identity resolution and the product recommendation part. Yeah.
Great, thanks, Yogesh. And I should add that if you have questions to ask, please just ask them in the Q&A button that you'll see in Zoom. So let's get started. So we're going to talk about identity resolution, and we're going to talk also about why Hopsworks and Infrix for ML identity resolution. We'll do a demo in Infrix, so a no-code demo for developing pipelines, and then we'll build an application on top of our identity resolution solution, which is personalized recommendations, and we'll do that in Hopsworks. We'll take any questions at the end. So identity resolution is a very big problem. I think everyone who's on the call at least is aware that accurate and complete identity resolution is very important for protecting businesses from loss, from fraud and security breaches. Privacy concerns are very important, that you identify who your customers are so that they trust you and you don't damage your reputation or any customer relationships. And of course, it's difficult in managing all these multiple identities, because if you have problems or complications in identifying users, it can be inconvenient or it can be worse, loss of business reputation. So it's important to manage identities and to identify users who visit your services. And you need to carefully consider the costs and benefits of implementing an identity resolution system. So it's not a trivial problem. I'm going to jump in straight ahead with something new as well, why I think identity resolution also has a large role to play in large language models. So currently in large language models, people talk about doing something called retrieval augmented generation. They want to go out and find some external information from the prompt that the user enters. This is the question or user input that the user provides. And often you'll see people say, go to vector databases to find some similar documents. But in fact, if you have an application that's providing a large language model, identity is probably the most important thing that you can have, a user identity for unlocking enterprise data. So if you're able to infer or with high confidence understand the user's identity, and you have information about that user on your platform, then you can retrieve that information and you can use that information then to build richer prompts. This is called retrieval augmented generation in large language model territory. And then we can make what we call personalized recommendations and personalized questions to large language models. That's also another new area of really exciting application of identity resolution. But there are a lot of challenges in identity resolution, in particular data challenges. So when people come and visit your service or use your service, they may engage in transactions, visit a website. It's very rare that stores have unique identifiers for people and parts. There'll be lots of crumbs of information available for you that you need to stitch together to get to determine the user identity. So there's no specific information about a customer. These fragmented, and often you'll have many different identities for a user online. Maybe if you have an account on a social media platform, you may have one username there and a different username at your company and a different Gmail address. So rolling up all insights about users, individual users, becomes difficult and accurate unless you can resolve these ambiguous identities and pull them together to ensure you've got a coherent, cohesive view of who these users are. And that's, of course, challenging given many people have multiple email addresses, usernames, credit cards, and then they can even pay with things like crypto. Now, in particular, graph databases have been a key technology of implementing solutions for identity resolution. One of the challenges with graph databases, however, is when you have developed some algorithms, and we'll look at some algorithms in a minute, for establishing user identity, resolving user identity, I should say, how do we then make that data and that code available and the identities that are being created to online applications? It's a very big challenge. So if you're using a graph database that has a data science platform inside it, and you figured out some code and some static data, data dump that you have, and you figured out that this mechanism that you've developed, these algorithms you've developed, are very effective, how do you plug that into your online system? And that's where we'll see where the feature store in Hopsworks is a key enabling technology to connect the back end where we have our graph databases with the online applications that can retrieve things like pre-computed features at very low latency without having to spend maybe, over your SLA for your online application and trying to resolve an identity. So we'll get into that in a minute. Okay. So I mentioned that graph databases have been a key technology in establishing identity. And one of the reasons for this is because they're able to build what we call an identity graph. So an identity graph is when we put together different identifiers into a unified view of people. Often we'll consider more than just an individual person, we'll also consider the household that they belong to. And we'll see later that you can have issues such as, several people in the same household using the same device, having many devices within a household, and how to disambiguate from one person to the other, even if they're using the same shared device. So when you get an identity for a user, this identity resolution will enable you to personalize content. We'll look at personalized recommendations as an example later. It also helps to give you unified customer experience. So if we can establish the user's identity very early, then even if you're connecting to a service from a laptop, a mobile, or even from some physical location, we can give this unified customer experience, which is high value for enterprises. And then finally, I mentioned already that establishing user identity can unlock enterprise data through retrieval augmented generation for large language models. So identity resolution will help with a lot of higher level problems. So customer 360, personalized recommendations, fraud, prevention detection, secure customer authentication, compliance with privacy regulations, improving customer experience, streamlining operations, preventing against data breaches and cyber attacks, and very importantly, building trust and maintaining a positive reputation with customers because you know who they are. So let's have a look at some of the details then of how we can develop algorithms for identity resolution. So the first point is that we need to have some sort of base for identifying identity. So we need to have our data available, and we would have typically a graph database outside of the context of what I'm showing here. So Hopsworks does not have a graph database, but there are many graph databases out there, and Infrix, our partner with Neo4j. But once we have a graph database, can be used along with a lot of the information we collect about users through the Hopsworks feature store. That's a data platform for managing your data for AI. Now, once we have this data available, we can build a lot of ML-driven applications, and I'll talk about personalized recommendations today. We also have anti-money laundering, credit risk, customer 360, and many more. So let's dive into some of the details of the challenges that we have and the solutions that we have. So ID resolution challenge number one is that we need, if we have unique identifiers for people, that's great. We can manage them in a platform called a master data management system. And it's not just for people, we can also have it for corporations or products and so on. Often we'll also have ambiguous identifiers. So it could be the name of a person, it could be their address. Often they might be spelled a little bit wrong or slightly different. And maybe somebody has a middle name that they leave out, or that they just put in so Jim P. Dowling. So you put in the first letter for your middle name instead of your full middle name. And sometimes you'll have no identifiers. So if somebody may be coming to your website and there won't be any crumbs, they might turn off JavaScript and turn off cookies. So these are some of the challenges we'll face, and How do we build an identity resolution model with machine learning? Well, I mentioned already that with building a graph of all these crumbs of information is a very useful way of establishing confidence in the identity of a user. And we'll look at a couple of techniques in a minute. But what the graph can take into account is the network of attributes. And each of these attributes or crumbs will contribute a relative amount of information to the overall establishment of identity. So it helps to resolve ambiguous identity. So if you have a node in a graph that has many links with name and address and date of birth and social security number, and some of them are missing and some of them are slightly different, but if they match up with other communities of identity of that same user, then you can have high confidence that that is actually the same person. And there's other pieces of information such as text features. Traditional text-based approaches are Levenstein, Jarrett-Winkler, Sorenstein, distance. They're quite useful, but they're not always great for anonymous web visitors. And then finally, you have online predictions. So in an online application, when somebody is maybe doing something on your website, clicking on links, watching videos, and so on, all of that data, those events, can be streamed into an event bus, such as Kafka or Kinesis, and streamed back into a platform like Hopsworks, an online feature store. And that data can then be made available through the online feature store at very low latency. So within a second or two of the user taking action on your device or on the website, that information will be available to help us resolve the user's identity. So between these three different components, graph features, text features, and online state that we collect about users, we can quickly help identify who the user is with the help of machine learning. So let's look at a graph-based approach. It's called weakly connected components. We have a user here, Johnny Johnson. And Johnny, we can see, has many, she's a node in the graph. Here we can see there's many different edges to different pieces of information. We have an email address, telephone number, an Amex card number. Excuse me. And we can see we have a home address and so on. And then we can see some links. We can see some weak connected links to other people that we haven't identified. And we can see some other pieces of information or crumbs around them. So context here can be used to derive identity within a community. So we've got a group of community people with shared context. And this helps narrow down from the very large scope of potential identities that we have to this person, Johnny Johnson, belongs in this community. And from here, we can actually then recursively further distinguish between the people who share these attributes within a weakly connected community to create more accurate, what we call Louvain communities. So this is an iterative process where we have Johnny here, and we basically can then work our way through with the recursive Louvain to recursively remove a lot of the other nodes in the graph until we establish that Johnny is the person in question. And we can imagine that there's somebody else here, John Johnson, who maybe is a partner to Johnny, and they may share the devices that are being used. They may share some of the address and so on, and that helps us as one of the techniques to help us recursively identify who this is, this node in the graph. Now, let's move on to Hopsworks. So why do we need Hopsworks in this scenario? We mentioned already that the graph databases that can compute weakly connected components and recursive Louvain, those pieces of information can be done sometimes they can be done in relative real time, depending on how big your database is, but sometimes it may take tens of seconds to compute that. So in that case, having pre-computed information in Hopsworks enables you to retrieve as much information as possible to do that identity resolution, either directly in Hopsworks, or if you don't have too much data, you can call out to an external graph database like Neo4j, and with some of the event data that's being collected in Hopsworks in real time. Now, Hopsworks as a platform enables you to do both batch machine learning and real-time machine learning. And when I say to do, I mean to both develop and operate machine learning systems that are either batch, that means they run on an interval. You have a machine learning application that maybe runs once a day or once a week, or it could be a real-time system that's user-facing, maybe on a website or a mobile device. So Hopsworks enables you to plug in many different data processing platforms or pipelines. You can write them in Spark or Pandas or Flink or SQL, and it has very low latency access to retrieving this pre-computed data that's being collected in real time. and that enables real-time identity relationship and resolution, compared to other platforms that maybe only can do this offline. As a platform, Hopsworks can be deployed on-premise or managed in the cloud. So if you're not on the cloud yet, it's still a viable platform for you. And then Hopsworks has support as well for GPUs. We have support for both training and doing inference. So K-serve is built into the platform. That's the Kubernetes model serving architecture. So you can deploy the models that are using, for example, the identity resolution component in the same platform, which is very beneficial. Hopsworks internally also includes both a feature store and a vector database. Now, how do we build machine learning systems in Hopsworks? Well, machine learning systems in Hopsworks are modular ML pipelines. We compose a machine learning system out of three main parts. The first part is the feature pipeline. Now, in this case, if we are pre-computing identities of users, or if we're going to resolve them at runtime, we have to have the data coming from somewhere. So the data typically might come from a graph database for the graph features. For other features, the data may come from other sources. The feature pipeline will take this data and output features and labels. And those features and labels are used by the training pipeline to create models. So with features and labels and supervised learning, you can train a model. The features themselves can also go to the inference pipeline to make predictions. So a model and features together output predictions. And these are the three pipelines together make your system. Uniquely, Hopsworks allows you to pick and match the tools and technologies you want to run these pipelines. So you can write them in Pandas, Spark, or Polars, DBT, Flink. And training is typically implemented in Python, and inference can be Python or Spark are the most common options. And you can also even run your own orchestrator for these pipelines. They don't have to run in Hopsworks. If you have your own platform for doing that, that's completely fine as well. So together, when you put it all together, a machine learning system on Hopsworks will consist of a feature pipeline, a training pipeline, an inference pipeline. They can run inside Hopsworks or outside. And then we have Hopsworks to manage the data, the state for the features that are used for training, and then the features also used for predictions. And then the model registry, Hopsworks has one, which is tightly aligned with K-serve, the model serving framework for Kubernetes. But you can, of course, use an existing model registry if you have one already. So as Hopsworks is an enterprise platform, a lot of the challenges you have with respect to bringing another platform into your organization, Hopsworks is deployed at many very large enterprises, Fortune 500. So cost-effective, efficient, audited, explainability, security, regulatory compliance. We have both SOC 2 and ISO 27001 compliance, SOC 2 Type 2. So that means it's also GDPR and HIPAA compliant, CCPA compliant. And then there's extensive support for governance. So you can define metadata, custom metadata about a lot of your attributes, your machine learning assets, so models and features, defining the scope in which they can be used. So you could say, for example, this particular feature cannot be used in California due to CCPA non-compliance, or this model, its data can be retained for this period of time, and so on. And maybe this data has personally identifiable information. So that's all built into the platform. So we're going to move on, and Yogesh is going to start by showing the no-code approach to building pipelines for generating these graph features. So we saw earlier that we talked about using weakly connected components in Louvain to start from a large volume of potential identities to whittle that down and reduce it with weakly connected components, and then recursively applying Louvain to establish ultimately identity. And then that data can be stored in Hopsworks, from which we can then go and build an ML-driven application that builds on user identity. In this case, we're going to demonstrate personalized recommendations in Hopsworks. So I'll hand over to Yogesh at this point.
Thank you, Jim. Let me share my screen. Okay, I hope you guys can see. So this is the interface to log into Inferix. As I mentioned, Inferix is a no-code or a low-code application development accelerator. So we have used Inferix to build the application that I'm going to demo, which is running on the top of Hopsworks and graph database, which is Neo4j. So once you log in into the system, you can have one or more applications. Depending upon your access rights, you will have access to these applications. So this particular demo I'm going to do as a part of the customer analytics application. So the goal of this application is to analyze the customer data, and then basically use all those breadcrumb information as well as the properties on the customer data to identify the common unique customers using the algorithm that we just spoke about. So there is a pipeline which will actually demonstrate like what are the steps involved for identity resolution. I'm going to zoom this in. So using Inferix, you will be able to basically invoke these algorithms, which are graph algorithms. So in this particular case, what we are doing is the data is fed into Neo4j, which is a graph database on a real-time basis. And then once the data gets fed, we take a projection of the graph, which means we don't want to take the full graph, like every node and edge, to run this community detection algorithm. We take a slice of it, the nodes and edges which are relevant for this particular problem. And then once you do that, then we run that data, the projected graph, through the WCC algorithm, which is a weakly connected components. So it's going to generate multiple communities, one or more, depending upon how many unique customer it is going to identify for you. And then, as we mentioned before, we are also using the recursive Leuven algorithm, which is to optimize this community. So for example, it could be an husband and wife sharing the same device, but it may be or two people sharing the same device in a public restaurant, and that doesn't mean they have any connection. So we need to kind of optimize. We need to take another look at those entities which were resolved by the WCC and see if those entities are really unique or they should be split into newer entities. So with the help of these two algorithms, we should be able to distill it down to cleaner, unique entity data. Once the entities are defined, then we can basically, now we know a unique identity of the customer. Now, with the help of the customers, the purchase pattern or any pattern they may have, the transaction pattern, we can start predicting. We can train a model for product recommendations. The goal of this application is to uniquely identify the customers and then train a model using one of the recommendation algorithms. And then once that is done, then we do a recommendation of the products. So the features that are generated out of the communities are stored back into Hopsworks. And once the model is trained, that also goes into the model registry of the Hopsworks. And then finally, this model can be used for product recommendation, both in real time and batch. So all of these steps can be achieved through point and click using this tool. You don't have to write any piece of code. And then finally, you can kind of visualize all the outputs. So we can create a quick dashboard, like a customer 360-degree dashboard, which allows you to see what do we want to recommend. So this particular case is on like banking product data. So I'm going to pick a customer from here. And then you can draw like different types of visualization. So for instance, you can show all the personal information that is present on the customer record. You can show the employment information, the banking relationship. So these are the existing relationships, the products the customer is already using. And then what are the other products available in the bank? And then any kind of sentiment analysis, the sentiment score, quarter over quarter. And this is the recommendation I was talking about. So right now, see, what we are really recommending is the products that the banks are offering. And these are the products which the customer is not using today. So we have a very high degree of score on debit cards. So this is something that we can recommend. So all of this is possible, like the visualization, the algorithms, the feature generation, storing in and out of Hopsworks can be done through this platform. Okay. Back to you, Jim. Thank you, everyone.
Thanks, Yogesh. Right, let me share my screen. Here. So yeah, we did a little bit of visualization already. Okay. So let's move on and look at personalized recommendations in Hopsworks. This is quite a big area. One of the things about personalized recommendations is that there are many different architectures for building personalized recommendation systems. The first thing we need, of course, is user identity. Otherwise, we're not able to store user features, preference, and history. And when a user is on a website, for example, and we have items that we'd like to recommend, we need to also save a history of when we recommended items to users, which items did the user either click on or potentially purchase. So that training data we can assume exists. And when that training data exists, we can train, this is called a 2-tower embedding model. This is the state of the art for real-time personalized recommendations. And it's done at scale at most large retailers today. And what you basically do is you take all of the products or items that you have and you train something called an encoder with those items or products. And with this encoder, what we can do is we can create an embedding from a description of an item. And we also train a query encoder for users. When a user types in a query or when a user maybe clicks on a link, we'll take the preferences of the user, the history of what they've done. We're going to convert that or squash it all into what's called an embedding. An embedding is just a vector. It's an array of floating point numbers with a fixed size. The embeddings by the user queries that are generated and the embeddings generated by the items or products will be the same length. They'll be in what we call the same embedding space. So what the 2-tower embedding model does is it's a way of training both the item encoder and the user query encoder with the same training data. So the training data here is a user clicked on an item. This was the user's history at the time when they clicked on it. These are the features related to the item. So it might be the name of the product, the category, the price, and so on. And this training data then is used to update these models. So what we're looking for is if a user was searching for shoes, for example, and then we have an item which is a pair of sneakers, they'll probably be quite close together. And if they're not close together, it might be because the user didn't click on it. But if the user clicked on it, then what we expect is to have a lower loss function. So this training process basically reduces the loss between items that users have clicked on or purchased, and it updates then the weights in these models. We end up with 2 encoder models, a user encoder and an item encoder model. So when we have those models, we can then go ahead and build what's called a retrieval and ranking architecture. And you can build and run all of this on Hopsworks. All of the platform support is here. And how it works is that the user, basically, we have to have the user identity, of course. So that's where the key starting point is. When we have a user identity, we can enrich that user identity with features. We can go to the feature store and say, here's history of the user, here's what they liked, here's what they purchased, and so on. And using that history, we can then run it through an embedding model. Firstly, it'll be the query embedding model, the user query embedding model. So the way it works is as follows with architectures, that the user will maybe click on something or maybe they'll enter some text. We'll retrieve the user identity, as we showed earlier with Yogesh. We'll determine the user identity with identity resolution. And then with that user identity, we'll retrieve more information about the users that we can then push into our embedding model that we'll deploy on a model serving framework in Hopsworks called Kserve. Kserve is the de facto model serving framework for Kubernetes. It's open source. And then we'll have an embedding for the user query. And what we'll do then is we'll go to a vector database in Hopsworks called OpenSearch to retrieve the items or candidates that have that are closest to it. So if the user search for shoes, then we may retrieve sneakers and maybe loafers and other types of shoes. And we'll have a set of candidate items or products to recommend. And typically that number is somewhere between 150 and 350. You need to have some diversity in there as well, of course. And you may also have to filter out particular products because, maybe based on the user's age or based on their preference or things that have been blacklisted. Or items that users have bought before. You don't want to recommend them again. But after we've done that, what we can do is we can take all of the products and we can go back to the feature store and say, hey, I got all of these IDs for the products, but I don't know the features for the products. I don't know the color of the shoes. I don't know the brand name and so on, the price. When you retrieve all of those features from the feature store, we can then rank all of the shoes or items for this user. So this is another model called a ranking model. So we send a request to the ranking model, post it on Kserve, and we'll get back a set of ranked candidates. And all of this needs to happen in less than 100 milliseconds or 200 milliseconds. So it's very much a fan-out architecture. There's quite a lot involved. This is the operational architecture for building it. So let's have a quick look at the demo in Hopsworks. So let's jump back here. So in this case, I have some tables of data that of features that we've built up. So there's actually an offline component to this. So in the background, we'll have a feature engineering pipeline. Here we have one here that reads data about the transactions that have happened, the customers and their identities, and the articles that they bought or looked at, and so on. And this code here will basically write all of that data to the platform Hopsworks, the feature store. And this data gets updated every time the pipeline runs. You can run them as batch pipelines. And I mentioned before, you can also have streaming pipelines so that they're updated constantly. So if we have a look at some of the data, maybe we can have a look at the transactions here. So these transactions are about customers purchasing items and the sales channel they bought them on, and so on. But we can see that we have some provenance data related to it. So these features are used to create this training data used in this model. We can get a quick preview of the data. So I'm a data scientist. I can look at the data quickly. We can see some activity on this table, or this feature group, we call it. And we can, look at statistics on the features. So we get some pre-computed statistics on the descriptive statistics of the numerical features here. So here you can see the price, for example, the minimum and the max is quite low price in this case. So this is how we create the features, and we'll be pulling features from Neo4j and the data created by Infrix will be pushed in here. What we then need to do is create some training data. So that's what we have here in the second notebook. I should add that all of this is available on our GitHub repo. It's public. If you go to the Hopsworks tutorials repo on Hopsworks on GitHub, you'll find it. And the next thing we're going to do is train our recommendation model using the two-tower model. So this is our two-tower model here, using a library called TensorFlow Recommenders for that. It also needs TensorFlow add-ons. And you can see all this code runs in Python notebooks and Hopsworks. You can actually run them as jobs as well. So these notebooks that we've defined here, I can actually create a job from them. So we can go in here in Hopsworks and say, hey, create a job from my notebook and schedule it to run every day, and so on. So for getting started, this is really great for data scientists. The barrier to entry is very low. If they want to install libraries, you can see you can do it in the notebook here, but this notebook is running on a container in a connected Kubernetes cluster. If I want to install more libraries and have them persist, we have support here as well for your Python environment. You can go ahead and install libraries here as well. Okay, and you can check out your code in Git and Hopsworks and all the kind of good developer stuff that you would like. So in this case, we're training our model with the two-tower embedding model. And if we step through it here, we can see that we've now trained it. We're going to deploy it to the model registry in Hopsworks. So in this case, it's a TensorFlow model, and we're saving that model to the local file system, and then we're going to upload the model. So this is where we actually create the model. It's a TensorFlow model in Hopsworks, and it's in this directory called query model, and that will basically write the model to Hopsworks. So we'll see that model in Hopsworks here. This is the Hopsworks model registry. So this is the query model. And we can see the model was uploaded. We didn't deploy add any metrics in there. You can store metrics with it. We can look at the files that were uploaded here with it. You can even see the copy of the notebook used to correct it and some sample put data for the model. But if we go back, we can see this model is also used in a deployment. So this model is actually being deployed. So we jump down here, we can see this is our model deployed in Hopsworks on Kserve. This is our query deployment model. And, if we have a look maybe in the last hour, I think I might have called this model at some point. You can see at some point here, there was some activity. It might be in the other model I was calling. So quick look, the ranking model. Okay. So this model, all these models here in Hopsworks are deployed on Kubernetes. And what we can see here is just some activity on the model. So they're being called, and you can test them here. And we can see logs and metrics. So the metrics are stored in Grafana, and then we have logs stored in OpenSearch. So you can see the logs of the model as they're actually run. So if we go back and look at our notebooks, we've got a bunch more notebooks because we also had to store the data in our vector database or OpenSearch in this case. So in this particular notebook, we populate OpenSearch. We build the index of our products in OpenSearch. So this is happening here, and we're using the FICE index. And so you can see it's populating all the products in our OpenSearch instance. And then when we want to actually deploy the model in real time, what we'll see is, if we have a look at the, we go back to our query model here, you can see here, and then down to our ranking model. So we have the ranking model. We can go through briefly, but this is creating a model that will rank all of the products based on the user features. And this is a very simple model. So this model is being trained. The goal of these models is to be fast, because you're going to have a lot of parallel requests. You maybe have 1 to 300 input feature vectors that you want to make predictions with, and so you need to be fast. You'll pass a pandas data frame to make it go faster, but if we look at the model itself, this is our ranking data set. That's not the actual training of the model. So this is that was creating the data set for it. This is using CapBoost to train the model. So CapBoost is a very low latency model. You can pass in a few hundred feature vectors, and it'll make predictions in a couple of milliseconds. That keeps us within our latency budgets. And you can see the performance is relatively, not great, but good enough for what we need here. And we upload our ranking model to the model registry. And then finally, we need to create the deployments on Kserve. So if we look at the deployments in what we're doing in Kserve, is we're also adding something called a transformer. And this is when the request arrives to Kserve, this transformer will receive the request. So the request will be received here, and then it will call the model. So in fact, what it does first is it calls the you can see it looks up the candidates in OpenSearch first, and then after it's got its candidates back, it filters out users who bought the items already, and then we basically build up our features from the feature store. We're going to retrieve all of the features for the articles or items that were returned by OpenSearch, and then finally we're going to we get back our articles data frame here, and we merge them together with the items, the user query items, and then we're going to call again. We're going to call it'll pass it on at this point. Sorry, at this point it will then pass it on to the predictor component. So the predictor is down here. This is our predictor here, and the predictor will rank all of them. This is going to be the model that we've downloaded, our ranking model, and it will take in the products and features, and using then predict prob A on the set of features, it will return the ranked scores. So there's quite a lot going on here, but but this is basically what you need to do to get to the state of the art. Okay, so that's pretty much a quick overview of how you build this retrieval and ranking architecture and deploy it on Hopsworks. There's quite a bit more to it, so you can contact us if you want to go a bit deeper into the demo, or a bit more to the details where the devil is. But it gives you an idea of some of the potential you have when you have identity resolution in your platform. So if we put this all together and talk a bit about how Hopsworks and Infrix together enable you to build ML-driven applications, well, we can see that Infrix has this low-code ability to build applications and pipelines on top of Hopsworks, whereas with Hopsworks, we have these capabilities of building applications we saw in Python notebooks, but also Spark and Flink and SQL are possible. And Hopsworks provides a lot of capabilities then. We saw the user interface with our ML registry and the development and the monitoring, auditing, and logging capabilities in Hopsworks. Hopsworks model registry is designed also to manage very large foundation models. And then there's a lot more capabilities in the platform that are highlighted in here. And one thing that that's not included, that you would need to include for the identity resolution problem, is a graph database. So that's it for the moment. I see there's a couple of questions, so I'll take the questions at this point. So we have an anonymous attendee asks, if I develop my features on Neo4j graph data science, and I'm not sure how this would all work with Neo4j, can you please explain? So if you're developing graph features in Neo4j, one of the issues is how will your online applications, such as the recommendation system, retrieve those at runtime? So there's two ways you can do it with Hopsworks. One is that you can pre-compute features, so you can pre-compute identities and other features and write them to the feature store from Neo4j Graph Data Science Toolkit. So you can run programs in Neo4j GDS on a schedule, and then those features become available at low latency from Hopsworks feature store. The other way is that if you don't have too tight SLAs, in the models that are deployed in Hopsworks, we saw we have a transformer in Kserve. This is where the request arrives. We can make a request to Neo4j to retrieve, for example, to estimate, not to estimate, to compute a user, or resolve a user identity. So we could go to Hopsworks to retrieve as much crumbs as we could about the user, and then using those crumbs, make a call on Neo4j to resolve that user identity. Again, using the algorithms we looked at earlier, such as weakly connected components in Louvain, if you don't have the SLA, if the SLA is not that bad. And then those are the two main ways in which the platforms can be integrated. So another question here, which is, can you use a vector index of a graph database instead of or along with OpenSearch vector database? Of course, so we see more and more databases are adding vector database capabilities. So Hopsworks internally has support for OpenSearch, and OpenSearch's vector database is effectively an index called FAISS. And FAISS, F-A-I-S-S, was a library developed by Facebook. There's another one called Hierarchical Small Worlds Networks library that's also supported by OpenSearch. And you'll find that most of these databases like Postgres and Neo4j support the same, either one or both of those two libraries. So there's not, I would say, a huge amount of innovation in terms of new indexing libraries in the vector database space. There is another one by Google called Scan, but we see most of the commercial vector databases all have the same underlying engine. So the answer is yes, of course, you could plug out and use Neo4j's or Tiger Graph's vector index if you wanted to. There's not really, they're all pretty much interchangeable and the performance is all pretty similar. If you're curious, there is a website called ANN Benchmarks where you can compare the performance of a lot of these different vector databases. Okay, then I think we're done. Thanks very much, everybody, for attending. If you want to find out more about Hopsworks, you can visit our Slack, public-hopsworks.slack.com. Go to our website, hopsworks.ai, and we can tell you more about how you can solve identity resolution problems with Hopsworks and Infrix. Thank you very much.